Okay, so I'm going to get started. Today's announcements are that Sapling Chapter 1 is due 9 a.m. Monday. Note that it is 9 a.m., so the start time of this class. Please don't email me during class and say, hey, I forgot. Also, the recitation quiz number 1 is next week in your recitations, so like all the quizzes, it's going to cover up through the end of lecture material today. And then I have a few people who have disability accommodations that allow them to have a note taker for the class. So basically, if you're attending class consistently and your notes are really legible and detailed, send me an email and I'll put you in touch with Disability Services. And I think they give you like I want to say like $40 or $50 gift certificate to the bookstore at the end of the semester by way of thanks. So it's worth your while if you meet all the criteria. Okay, and then if you sign up for that, then basically you just have to scan your notes and email them out to the students on the list after every lecture. Okay, any questions about that? Yeah. Don't remember off the top of my head. It's still sort of a work in progress, but the quiz is going to be like one side of one exam. So it's basically designed, guys. Hey guys, you may want to listen to this. It's about the quiz. So the quiz is designed that you can get through it in about 20 minutes in recitation. So, all right. Okay. So that does it for announcements, unless anyone has any questions about these. All right, cool. So off we go, back into Chapter 2. So last time we looked at a few things related to alkanes. We looked at naming the N-alkanes. We looked at degrees of unsaturation. We looked at a few examples of functional groups. Before we go really thoroughly into naming, we need to look at one more thing, and that is substitution patterns. Okay, so this is basically just a way to label different carbon atoms and things attached to them by how many bonds they have to other carbons. Okay, so this is given with like the number of bonds to other carbons with a degree sign after it. So 1 degree means 1 other bonds to another carbon. We call that primary. 2 is secondary. 3 is tertiary. And 4 is quaternary. Okay, so let's put up an example structure here. Okay, so all of the carbons that are at the ends of any chain or any branch coming off of it only have one other attachment to carbon. So like this carbon here, if you remember we looked at skeletal structures last time, but this carbon here is only connected to this other carbon to the left of it. So this one would be primary carbon. Same for these 3 here, that's primary, primary, and primary. Then we have this one here, which has bonds to 2 other carbons, so 1 and 2. So that makes this one secondary. This one also has bonds to 2 other carbons, so 1 and 2. So that's secondary. And then this one here has bonds to 1, 2, 3, 4 other carbons, so that would be a quaternary carbon. Okay, so as it turns out, what degree of substitution or what substitution pattern you have on a given carbon will actually heavily affect the outcome of some reactions. There's some cases where the more crowding and stuff that you have packed in around the carbon, the harder it is for other stuff to get in there and react with it. We'll see some examples of this later. Okay, so this describes not only the carbon, this also applies to any hydrogens, any hydrogen atoms that are attached to it. So for example, if we have a primary carbon out here on the right end of the molecule, it's got one other attachment to carbon, it's a primary carbon, and all the H's attached to it are by definition primary hydrogen atoms. So all hydrogens on a primary carbon are primary hydrogen atoms. So that also affects their reactivity too. Sometimes it's easier or harder to remove an H depending on what else is attached to it. Okay, so that's pretty much the degree to which we're going to cover substitution patterns for now, but it is going to keep popping up over and over again in future. So it's good to get familiar with it now. Yeah?
So do those tell you anything other than how many bonds are on there?
Nope. And really, each of these carbons still has 4 total bonds. It's just how many bonds to carbon is what we care about the most. So, question?
Pi bonds count as
Good question. So the answer is once it's got pi bonds on there, we generally don't really use these substitution patterns anymore. This is more for single bonds to other carbons. So yeah, once it's got pi bonds, that actually behaves in a completely different way, so we call it something else. Okay. So I guess what I drew up here is sort of one example of something that is still an alkane, which is a hydrocarbon, but it's got a bunch of bits hanging off of it, all of these branching groups. So last time we looked at how to name N-alkanes, linear alkanes, where all the carbons in a row. How the heck are we going to name this thing? Well, that's what we're going to spend most of today on. Okay, so nomenclature. Which is basically just a fancy way of saying naming things. Nomenclature used to be a huge mess of just random names tacked onto things that people had discovered. Basically, you could name something whatever you wanted with no systematic influence at all. And then at some point in the 1800s, IUPAC came along, which is International Union of Pure and Applied Chemistry. And they decided this is not going to work. We need a better organized system than this. So they came up with this set of rules of how to name molecules that follows sort of a standard algorithm. So it's a systematic way of naming things. And we are sometimes going to see older pre-IUPAC names pop up, especially in really common solvents. But we'll cover those sort of as we get there. For now, especially for alkanes, IUPAC is pretty much the only system used. Okay. So a side note here, Loudon goes through these steps in a different order, and I don't really like how they split up the ordering of steps. So I've sort of reorganized and regrouped them into a way that makes more sense to me. But whichever method works for you, you'll get the same answer either way if you're following it correctly. Okay. So first up is figure out what the longest or the principal or the parent chain is. Okay, so we want, and these three things for the time being are being used sort of as synonyms. The longest chain is also the most important chain. That won't always be the case once we get out of the alkanes chapter, but for now they're the same. Okay. So once we find the longest parent chain, that's just going to be named after the N-alkane of the same length. So if the longest chain happens to be 10 carbons, we're going to name it as something, something, something decane. Okay, but the thing to watch out for here is that the longest chain might not all be in one horizontal straight line. It might bend and follow around angles, so you have to sort of check out different options sometimes. Okay, so here's one example. I'm going to draw this as condensed structural formula and then as zigzag formula. Okay, so that took a while to draw. Much easier if I just do it this way. There. Okay, so this is the same thing, just to check. We've got 1, 2, 3, 4, 5 carbons up top, 1, 2, 3, 4, 5. And then we've got this 2 carbon bit hanging off one from the end, so 1, 2, 1, 2. Okay. So I'm just going to stick with skeletal structures for the rest of these examples so I don't have to write so many C's and H's. Okay, so looking for the longest chain, you might initially think, okay, 1, 2, 3, 4, 5, it's a pentane-based something or other. But if we go down here, 1, 2, 3, 4, 5, 6, we can get a 6-carbon chain as the longest in the structure. Okay, so in the notes, I use bolding to indicate the parent chain. In the board, rather than bolding, I'm going to draw like sort of a bubble around the whole thing. There we go. At least for this condensed structural formula. So that's a 6-carbon chain. This would be named as a derivative of hexane. In the skeletal structure, we can see the same thing. So again, counting the bends or the ends of the line, I've got 1, 2, 3, 4, 5, 6 carbons. So it's a hexane derivative of some kind. Okay, any questions about this example? Okay, cool. As kind of a follow-up complication to this, sometimes we have multiple different options of how to get the longest path. So if multiple paths both have longest chain and it's contested, then what we're going to do is choose the one with the more branch units coming off of it. Or in other words, with more groups attached directly to the parent. Okay, so here's 2 copies of the same molecule. So I got a 6-carbon chain with a 1-carbon bit there and a 2-carbon bit here. 6-carbon chain with a 1 and a 2. Okay, so I have 2 different ways to find the longest chain here. One is I could go 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Or I could go 1, 2, 3, 4, 5, 6. Okay, so both of these get me 6 carbons as the parent chain. You might also be asking, could I have done this at the end? At the left end, I go down instead of out to the left. And yeah, that's also a totally valid way to find the longest chain, but it gives you exactly the same connectivity as up here coming off of the parent. So you can draw either one and have it be the same. Okay, so between these options and this option, this one only has 1 group coming off of the parent chain. Whereas either of these ones have 2 groups coming off. So this option over here is the better choice. Okay, so questions about that? Yeah?
You said the better choice.
Mm-hmm.
Well, never mind. I just read it. Sorry about that.
Okay, cool. Yeah. Yeah, so when I say better choice, I guess I just mean like the correct one to make according to IUPAC. Yeah. Which really IUPAC is just a set of rules that people came up with that's kind of arbitrary, but yeah, it's not anything to do with what the molecule itself wants thermodynamically or anything. Yeah. Okay, so once we've got our parent chain figured out, then we've got to start throwing numbers onto the carbons. Actually, no, sorry, I'm skipping ahead. What we're going to do next is name the groups coming off of the parent chain. Okay, so these groups are going to be named after whatever N-alkane that they're based on, basically the thing with the same number of carbons. We're going to drop ane from the end of the name, and we're going to add -il to the alkane name. I'm going to change boards now. Okay, so for example, if we have a 1-carbon group hanging off of the parent, 1 carbon is the same as methane, but it's not like a full-on methane molecule anymore. It's methyl as a substituent. If we have a 2-carbon group hanging off, that's ethyl, and so on. Okay, so I'm actually going to just draw like a huge long parent chain all the way across the board here, just to give me some places to start attaching substituents onto. Yours doesn't have to be the same length. I'm just doing this to give myself space. Okay, so this one here is a 1-carbon group. That's methyl. This one here is a 2-carbon group, so that's ethyl. And I could keep going with like propyl and butyl and pentyl as just like straight chains of 3, 4, 5 carbons or so forth. I'm not going to draw all of them exhaustively, because I'm going to also show some ones that are not based on N-alkanes that we also need to know. So some of these you just have to learn, but I'll cover ways to remember them in just a second. Okay, so this one here, the carbons are not attached in a straight single line coming off of there, but there are 3 of them. So rather than calling this propyl or N-propyl, I'm going to call this isopropyl. This group also features in isopropyl alcohol or rubbing alcohol. Okay, we can also have something a little bit similar, but with a 1 extra carbon in there. Again, it's not a linear, normal butane-derived group. This is isobutyl. Okay. We can also have this one. Which is Sec-Butyl. We can have this one, which is tert-butyl. We can have this one, which is now 5 carbons, called neopentyl. And here's an example of a cyclic one. I chose a 6-membered ring hanging off of here. So this would be cyclohexyl. Okay, so a few tips on how to remember these. One is that anything that starts with an iso has an extra methyl branching off right near the end. It's got this little like robot pinchy arm thing going on. So like isopropyl has that, isobutyl has that, and then it's just got some extra carbons linking it to the parent chain. So that's how to recognize isogroups. Sec-Butyl and tert-butyl, telling those apart, it really helps to remember where these names come from. Sec-Butyl is called that because it attaches, if you ignore the attachment to the parent chain, that is a secondary carbon. It's got two other attachments to carbon within its group. The reason we ignore the parent chain attachment historically is because this is still a sec-butyl group if it's attached to something that's not like a long carbon chain. Like this could be an alcohol group or like a bromine or something, and then it would be like sec-butyl alcohol or sec-butyl bromide. Similarly, this is tertiary at the point of attachment, ignoring the parent chain again. Okay, so a secondary butyl and a tertiary butyl. Neopentyl, no idea where that one comes from, honestly. Neo means new. I guess that's where that comes from. And then cyclo, obviously it's in a ring, so that's kind of where that's coming from. Okay, so one other thing that looks kind of trivial, but that is actually crucial in the next step that we're going to look at. Some of these prefixes on groups are hyphenated and some are not. So note that anything that's based on a substitution pattern name, sec and tert, those have hyphens in the middle there. Everything else just sticks straight onto the name. So like iso, neo, cyclo just runs straight into whatever the name of the group is. Sec and tert, you got to hyphenate. Which matters because some of those get counted when we're alphabetizing groups and some of them do not. Okay. So, while we're here, there is actually one other useful thing that's going to pop up that Loudon doesn't cover for a while yet, but is worth kind of mentioning here. And that is that most alkyl groups have 2 to 3 letter abbreviations. And so a lot of the time, instead of writing the full word methyl group, we'll actually show methyl is ME, ethyl is ET, propyl is PR, and note that propyl is the first one where we have to worry about different shapes of the groups. Like we pretty much only have one option for methyl and ethyl. But propyl, if we want to specifically say it's not isopropyl, it's regular straight chain propyl, we can throw the N for normal in front of it. Same for butyl. And then all of these weirdo groups that I drew up here as examples pretty much have like the same 2 letters for the number of carbons, but then they have a lowercase letter in front of that. So like isopropyl is a lowercase I. So lowercase I, capital PR, which looks like it should be some kind of Apple product, but it's not. Isobutyl, IBU, Sec-Butyl is lowercase SBU, tert-butyl is lowercase TBU. We'll see a fair bit of that one show up later. And then neopentyl is NP, and cyclohexyl is CY. And to be honest, these last two, I had to look them up just for the sake of completeness, but these are less frequently used than the other ones that I've written up here. Okay. So all of these groups you might see written out as their shape, you might see written as their full name, or you might see written as their abbreviations. So sometimes you'll see structures that look like, say, this, like the zigzag structure with an ET group hanging off, which we now know ethyl is 2 carbons. That's a 2-carbon chain hanging off of the bottom. Or you could have this molecule here, which is ethyl alcohol. You could abbreviate as ETOH, for example. Or you could abbreviate this, which is a tert-butyl group attached to an iodine, as TBUI. So this is an even faster way to write things out than drawing the zigzag structure if it's one of the ones that has like a 2 or 3 letter abbreviation. And this is also easier to type and easier to write on an arrow when we're doing reactions, so you'll very frequently see these written out this way. If you don't immediately know what that means, there's no harm in just drawing it out and then using that to figure out what's going on. Okay, so these are a whole bunch of alkane substituents, or alkyl substituents, I should say. One last thing that Loudon also doesn't cover quite yet, but I'm going to just squeeze it in here because it does show up in 1 or 2 sapling problems because it makes it easier to ask questions about naming, is halogen substituents. So technically this is taking us out of the realm of just hydrocarbons or just alkanes, but it turns out it follows the same naming rules, so we don't have to cover anything new here, pretty much. So we're just going to drop I and E from the end of the name, and we're going to add O. So for example, this is a fluoro substituent. This is a chloro. This is a bromo. And this is an iodo substituent. Okay. So that's how to name all of your substituents. Questions about this before we start putting it together? Okay, cool. I guess we can't actually start putting it together just yet because we have to do one more thing first. And that is step 3. We got to number our parent chain. Okay, so in general, all else being equal, we want to start at the end closest to a branch point. Or in other words, closest to the first substituent. Okay, so here's a real simple example. So a 5-carbon chain with a methyl hanging off here. I guess we've got 2 options on how to number our parent chain, or on how to pick out our parent chain, but I'm just going to go with, we're using all the carbons up top here as our parent. Okay, there we go. So we can number it carbons 1 through 5. In theory, we could start at the left, 3, 4, 5, or we could start at the right, 2, 3, 4, 5. But given that we want to start at the end closest to the first substituent, this option over here is looking better. This tells us the substituent is better put on carbon number 2 than it is on carbon number 4. Okay, so sometimes that'll immediately solve the question for us, sometimes it won't.
Which way do you go if you have two branches? Like say if you had another branch on the 2 and 4?
Yep, good question. So that's actually exactly the example I'll cover next. Yep. Okay. So, if both ends are equally close, then we want to pick the one with the smallest number at the first point of difference when we list the locations in order. So I'll go through an example of how that might look. So we want to pick the choice with the smaller number at first point of difference. Okay. Yeah, I think I can squeeze it in here. Okay. So, So 1, 2, 3, 4, 5, 6, 7. What if we put a couple substituents there and there? Can you guys see this bottom corner of the board? Okay, I think this thing moves up and down. Hey, wee. Okay, cool. Welcome. Okay. So this is an example of what was being asked just now. So here we have some substituents on the third carbon from the end, no matter whether we count from the left or the right. So I'm going to try numbering it both ways, and then I'm going to list the substituent locations and see which one ends up being better. So let's go from the left first. 1, 2, 3, 4, 5, 6, 7 versus 1, 2, 3, 4, 5, 6, 7. Okay, so if I number it this way, I got substituents at 3 and 3 because I'm counting these as two separate methyl groups coming off of the parent. So that one, and that one. So I got substituents at 3, 3, and 5. So 3, 3, and 5. Whereas if I do it this option, I've got substituents at 3, 5, and 5. Okay. So what I want to do is I've now got two sets of numbers. I want to go through and compare one at a time. So 3 versus 3, that's a tie. That doesn't tell me anything. Then 3 versus 5. 3 is the lower number here, so this option is better. So it's got the smaller number at the first point of difference. So this method on the left wins, which means that numbering this one from the left is the correct option here. And sometimes you might have like a dozen or so substituents, and then you just have to go through and compare everything pairwise till you find something that distinguishes them from each other. Okay. So questions about that example? Okay, cool. I'm going to erase the other side of the board real quick, so I'll take a minute. Okay, so one last note in this category before we move on to putting it all together. And that is that sometimes neither of these options is actually going to resolve it for us. Sometimes you'll still come out to a tie. So if numbering still isn't determined, then just start numbering at the end closer to the group that comes first alphabetically. So this is kind of our fallback option if all else fails. Okay, so for example here we could have this chain, and if we start numbering it from the left, 1, 2, 3, 4, 5, 6, 7. So we got a group on 3 and 5. Versus if we start doing 1, 2, 3, 4, 5, 6, 7, we got also a group at 3 and a group at 5. So that doesn't tell us anything. But now we'll have to start looking at these two groups. All right, so we got a 1 carbon group, that's a methyl, which we file under M. We got a 2 carbon group, that's an ethyl, which we file under E. So ethyl comes first alphabetically. We're going to start numbering at the end closer to ethyl. So we want ethyl at 3. So this one, numbering from the right, turns out to be the correct option here. Okay. So any questions about that example? All right, cool. So we figured out our parent chain. We figured out the groups attached to it. We figured out how to number. Let's throw this all together. So we're going to name our compound as location number, substituent, and we may have a bunch of these terms like number substituent type, number substituent type, number substituent type, and then the parent name goes at the end. Okay, so in general, everything is going to be separated with hyphens except the last substituent just runs into the parent name. Okay, so let's start out with like a relatively simple example. We already know this one. We're going to number as 1, 2, 3, 4, 5. All right, so the parent chain is a pentane, and it is a pentane that happens to have a methyl group coming off a carbon number 2. So this is a 2-methyl. Note the hyphens separating the number and the substituent location. And then now we can go straight into the parent, so 2-methyl pentane. Okay, if we got multiple copies of the same substituent, we don't have to do like 2, 4, or like we don't have to do like 2-methyl, 4-methyl. We can lump them together. And we do that by throwing a tri, tetra, etc. Basically the prefix for however many of them there are at the front of their name. But you still give the location number for each one. So for example, this one, all right, here's our parent. We're going to number it as 1, 2, 3, 4. I actually have several different equal options for the parent here, but I'm just going with this. All right, so I got a methyl group coming off of carbon number 2. I got another methyl group also coming off of carbon number 2. So this one I'm going to call as 2, 2 hyphen dimethyl. And then my parent is 4 carbons, so it's a butane. So 2,2-dimethyl butane. Another example that's almost the same but not quite. This one, it turns out not to matter at all which end I start numbering my parent from, because I'm going to have a methyl at 2 and another at 3 no matter what. So this one I could call as 2, 3 dimethyl butane, and I'm just realizing I did not move the camera over, sorry. There we go. Okay, if you're watching this at home, I'm going to move the board back down so you can screenshot. Ta-da. All right, and I'm going to move it back up. Okay. Okie doke. So pretty much we can lump them together if they're the same type of group. If they're not the same type of group, if they're multiple types of different groups, we want to give each one its own location number and then cite them in alphabetical order. And remember that to alphabetize, we do include prefixes that are not hyphenated, so like iso, neo, cyclo. But we don't include as the alphabetization things that are hyphenated like sec or tert, or any of these counting prefixes that we just covered. Di and tri don't get counted towards alphabetically. Okay, so how that might look. Let's do a longer chain so I can fit more stuff on here. Okay, so it turns out the longest chain you can get going here is 8. And the end closest to the first branch point is over here on the right. So 1, 2, 3, 4, 5, 6, 7, 8. So I've got an ethyl at 3, got a methyl at 5, and another methyl at 5. One thing you can do once it starts getting complicated is actually write the names of the groups and their locations in next to them, and then you'll have them all like in one place, and then you can go through and sort them out afterwards. So I'm going to write 3-ethyl next to this, and I'm also going to write 5,5-dimethyl to cover all the methyl groups on the structure. All right, ethyl files under E. 5,5-dimethyl does not file under D. We don't count counting prefixes towards alphabetizing. This one is going to go under M. So when we're putting this whole thing together, E comes first before M. So I'm going to list ethyl first. 3-ethyl, 5,5-dimethyl. And then that's all the substituents, so I go into the parent name, which is octane. Okay, so questions about that example? Yeah?
When submitting the ethyl or dimethyl kind of words, do you use a hyphen?
Oh, these from each other, you mean?
Yeah.
Yep, yes, so everything is split up with hyphens except the very last substituent running into the parent chain name. Yep. Okay, so I think that's a good place to wrap up. I'll cover cyclic naming and a couple more things next time.